Hello. This is one of the example that will be the one of the quiz on next Monday. So today we have mentioned that how to calculate electric field at this position P, electric field due to this line charge, and this line charge with the length L and minus Q. Well, in the class we proposed the line charge is positive. So here one of the suppose that the line is very thin, then you can ignore the effect from the y direction, so it has no influence in y direction. So in fact, just the 1D problem along x. So how to calculate this? Here, if we try to think that this line will divide it into very small pieces, and then each small pieces that we can calculate each field at this position P, and then we adding them from 0 to L, then we can calculate all the E field. So let's try to do, well, I can try to draw. This is the length L, and when we have the little dq, then at this point we have electric field like this. Then when we consider the next dq, then we have next E, next dq, then we have next E. Then when we get closer, for sure the electric field will be getting larger. Then at the last one we have the total E. So we have to sum at all of the electric field, then we can get the total electric field. Now here I should write the delta E because it's due to the delta Q induced has the electric field at this position, and with written delta E. So this total electric field at this position due to hold the line over here, then is equal to E, and we do the integration dE. Right? So the problem is how to write this dE. So first of all, we will try to do, we can see that at this little part dx, then with little dx, we can calculate integral from 0 to L. And at this time that we can think, if we have dx, then how much charge that we have in this little region. So first of all, we know O, we have minus Q, and the length of the line is L. So the length charge density is minus Q divided by L, and this we say this is lambda. So we know the density is lambda. So at this small region dx, the dq will be the density multiplied dx. So this dq, I say again, definition of dq is the how much charge that we have in this little region dx. Yeah, so we have this little dq, we can have one electric field. The next dq, we have next electric field. So we are going to calculate the delta E. So, well, here, yes, we know that the force, that Coulomb force, KQQ divided by R squared. But now we are calculating electric field, which means we want to know the environment that created by this line. So we ignore the test charge Q. So we have only KQ divided by R squared. Yeah? So this is the formula. So dEx will equal to K dq, because now we only see this little dq divided by R squared. So what is R? R means this little dq, the distance between this little dq to the position P. So this R will equal to, because now we assume this is L. The position from here to here is A. So here is L plus A. So if this position is x, okay, because we are going to integrate from 0 to L. So at this x position, we have x, then we have the positive, the charge, because now it's negative, so I just say charge. The charge is dq, then the electric field will be k dq to this position. So this position from here to here will be L plus A minus X. Okay, so I can try to write here to here will be L plus A minus X. Okay, so now we already have dE here. Okay, it's here. So when we try to calculate the whole electric field at this position P due to this one, then we can, K lambda will be constant, so it's independent of X direction, so we can take it out of the integration. And we know the region that we want to integrate is from 0 to L, the range. And then here will be the mathematical problem. We know this one, that L plus A minus X, this we can say as U. So the integration problem will be 0 L U square, and then here we should write the U. But from here the X is not equal to the U. So here, from here we can say the X minus the S is the U. Here derived by the X derived of U, so you can have this. So we know it's minus. So this one can be simplified to this one, and here will be very simple mathematical problem, integration problem. This will equal to U 1 over U and 0 to L, and because minus will be plus. Okay, and then here will be K lambda, and then here if we try to substitute U back to L plus A minus X, then we have the same formula here. Because TA jumps too fast, so I just somehow. Okay, so now you just try to calculate L. Here L will be L minus L will be 1 over A. When X equal to 0 will be 1 over L plus A. So here you can get this one, and will be this. Okay, so yeah, that's all. You can also substitute all these here inside, and then you can also solve the problem at the 13th problem in the textbook and in the chapter 22, just by taking the number of 8.15 centimeter as a L and minus 4.23 as a Q. You can try to calculate like that. Okay, so first of all, we easily to calculate the electric field at this position. So how about here? So at this position as well, we have to think dq, little dq. At this position, we have electric field along here direction, this electric field along this direction, and this. So you will write like this, right? And this will be here. So all these electric field, the sum of all these vectors will be in which way? So we can see these two first. If we have this vector, then the sum of this vector will be at this direction, right? Why? We can see in two ways. First, in this direction, we can decompose to y direction and x direction. This vector can be decomposed to this direction and this direction. This direction, when you sum two of them, because opposite direction, so we can cancel it out. But please, this E1, E2, it doesn't mean E2, E1 is symmetry. So E1 plus E2 equal to 0. No, it's not equal to 0. It's equal to E1 cosine theta. Sorry, if here is cosine theta, then will be sine theta. This will be E1 sine theta. Here will be E2 sine theta. So you will know that two of them adding two of the two vectors will be longer, and that's how you get the sum. Sorry, too long. So it will be like this. Okay, so will be sum of these vectors. So here as well, so you have lots of them, and you will see the horizontal component will be cancelled out. So the total electric field direction will be along this direction. So this is the total E, because the horizontal, all of horizontal will be cancelled out. Okay, once you know this, then everything will get very easy and will be the same as the previous problem. So first, let's try to jump to here. We have the point P. This distance is R. We have the length L is the same. Now we have the positive Q. No matter Q or minus Q will be the same. Don't really matter. So if we have the Q over here, then we see this distance R, then we have electric field. When we try to integrate from 0 to L, then we have from here to here, to here to here. Then here we do a trick. We try to integrate only half, only from 0 to 2L, because it's symmetric. So we know that the y direction, the electric field along this will be half, right? Because we are adding only from here to here. So the y component only growing half. And when we try to integrate the other one, the other part, then we are adding all these vectors until here, then we have double one. So if we only integrate half, the electric field only half. So now that's why we integrate from 0 to L divided by 2, then we only integrate half range. Then if we want to know the total field, the whole length L, then here we have 2 times. So here will be the same K dq divided by R squared, and integrate from 0 to 2L. And here, why we have the sine theta. So that's why I say, when you try to integrate, because this is a vector, right? And the vector in the 2D problem, let me draw. The vector in the 2D problem is not the same as the first one, the 1D problem, because 1D problem, when you're adding, is adding in one direction. So vector in one direction, in fact, you can treat as a scalar problem. But vector in the 2D problem, you have to decompose the vector along x direction and y direction in order for the easy calculation. And when you try to do both, here you can say here sine theta and cosine theta. And when you try to integrate from here to here, you will see that you don't have to consider the x direction, because when you integrate the other part, then the x direction will be cancelled out, only y direction. So if we have this sine theta, yeah, so this theta will be here, then this will be this one. So this will be here, theta. So this will be E, and this will be, the y direction will be E sine theta. So that's why when we try to integrate dE, maybe I can write dE right here. dE will be K dq divided by R squared. But this dE, you know, is a vector, and this vector is going to R. And here you will know R will equal to cosine theta x plus sine theta y, right? So each dE you should write like this, but you know cosine x, this vector will be cancelled out. Then it will become a 1D problem. So if that's why you can take off this y direction, because you already know that the final electric field will along this direction. So this will jump to here, and you don't have to think about the vector again because you treat it as a scalar. And finally, once you have the scalar, you know that it's, well, this scalar, once you know, then you can have the vector again, because you just take the magnitude and y direction, right? This is the vector because the magnitude along here and the direction is here. So here, that's why we have sine theta. Okay, and we take absolute value, so we don't need to think about the y direction. So everything will be the same. K take out because it's independent of r. And r, what is r? R is this distance from here to here. But we know this is L over 2. Here is r, capital R. So we know that this ones will be x squared. Oh, sorry. It's not 2 over L, sorry, because we integrate from 0 to 2 over L. Sorry, L divided by 2, yes. So when we integrate from here to here, the variable is x, right? So x will become, x is a variable. So when, for example, when we are here, don't try to mess up. So when we are here, not in the middle, the Q, when we integrate from this point to here, in the middle here is 2 over L, here is 0, here is point B, and this is R, right? R will from this point and integrate. When we shift the Q, then R will be changed as well. So this dq that will have another R plane, and this R plane will be another triangle, right? The theta will be different, R will be different, and here will be different. What's this? This is, if this is 0, and this will be x. Okay, so here will be 2L minus x, and that will be too much difficult. So now we did a trick. We treat this is 0. We integrate from here to here. This is x, and we integrate when we have at this point we think about the dq, and this position will be x. So here R, capital R. Then we can calculate R directly. R squared will be capital R squared plus x squared. That will be much easier than this, where this R squared will equal to this squared plus R squared. That would be much terrible. So that's why we calculate from this direction to here. And when we calculate only half, because we don't want to calculate from here to here, so we just 2 times double. Okay, so that's why we think at this position x, so R will be x squared plus capital R squared. And sine theta, okay, sine theta, what is sine theta? So try to know that we cannot ignore that, just integrate directly, because theta will change during the time. So now our theta is here, right? Theta will change over the time. So sine theta will equal to, this is theta, this is x, this is capital R, this is R. So sine theta will equal to R divided by R. R divided by R, but R will be square x squared plus R squared and root. Yes? So this and the x we can take here, R and lambda, take it out, and we can simplify the formula like this. And this, try to think about how to do that in your mathematics problem, finally we can get the result like here, and this one will be equal to these things. So it will be simplified like this: 2 over L, you integrate the x, so take 2 over L to x, and then minus the x value equal to 0, then you will get this formula. So this electric field is the environment that created by this line charge. And this one, if you don't know how to calculate it, then please try to think in this way. This is the hint. Okay, try to use this tangent. You will find that in your calculus lectures. And another thing is, I just want to talk about, like, try to think if this line is extend and it's infinity, then this point will be, we don't integrate from 0 to 2 and to half of the length, then we will integrate from negative infinity to infinity, right? So we will take this one, and this integration, if we take this, is minus infinity to infinity, then this part will be 2, then will be 4kq divided by r and root L squared plus 4r squared. So that would be easy as well. Okay, and then that's all. You can somehow read some notes from the TA, and that's all the questions, problems from the line charge. And the second one that we were talking about in the class, that about the dipole. So here we have positive, negative. So it's very easy here. I will go through very quickly. At this point, test charge, always we treat test charge as a positive one. So positive repel each other. We have electric field along this direction. Positive, negative, then we have attract each other. So we have this field along this direction. So this is again 2D vector problem. So we have to decompose the electric field along x direction and y direction. So this is one electric field due to the first particle. So will be E1 cosine theta, and this is 2 E2 cosine theta. So you will see here we neglect the sine theta. Why? Because along the y direction it will cancel out. Okay, so the first one will be kq divided by r squared cosine theta, and the second one will be k minus q divided by r squared cosine theta. So you just try to calculate. We calculate first the electric field due to the first one at first. Then cosine theta, what is cosine theta? Theta is here. So cosine will be x divided by r. X divided by r. Then r squared we can see is x squared and a squared. Okay? And r can be changed to this one. Then this totally will be here. And we know that if we add in this E1, the E1x component here, E1x will equal to this. The magnitude of E1x is here. And we know E2 will be the same. Why? Because it's one quantity, one charge. So the magnitude is the same, just the direction is different. So we have 2 times. Then we have 2 times this one. So that's all. And then first, this is the magnitude. Then if we want to write as a vector form, then it's magnitude here to here, and then it's along x direction. So we put the x head. So another one, it was about, maybe TA didn't write it here. TA didn't write it here. Okay, because it was written in the textbook. So please see the textbook. I remember it's 564 page, and it's talking about as well line charge, and then the point charge at here, and try to calculate the electric field at this position P. Okay, so that's all. This one is, oh no, it's not point charge, I'm sorry, it's the dipole. Okay, and then as well along this position. This example is at here, and then the sample in the textbook at page 546 is to calculate electric field at this point, the electric field of dipole. Okay, I found that in fact that the TA already wrote how to integrate this one, so well, you can stop it or you can try to look at it again. Because the problem of this kind of square root and so on, it's very difficult to calculate it, so we have to treat that x equal to r tangent u. So why we want to treat this is r tangent u? Yes, we can do it like this way. Okay, here. If we can take x equal to r tangent u, then we know that when we take into r squared, tangent square plus r square, tangent square plus 1 will equal to sec, right? That's why we can simplify this integration. That's the purpose to set the x equal to r tangent. So if we set r tangent, then we have this. But how to change the dx to du? So we know that x equal to r tangent u, then we do the derivation. Dx du will equal to r sec square. Okay, from here to here. Okay, so we know dx will be r sec square du. So this will be r sec square du. And because the r we can take out, it will be r squared 1 over r squared. And this will be, here will be sec power 3, here power 2. So total we have power 1 here at the bottom. And then this will be cosine. This cosine, the integrate cosine will be sine. So finally we have that this one will be sine u divided by r squared. Well, plus c, it's okay. So TA, ignore that. Anyway, so now we already have that. And how to change them back? Because we know x equal to r tangent u. And how to calculate sine u? I don't know how to take u as a function of x and r with our variable. So you know u will be arctangent x divided by r. Well, sometimes he wrote the capital R, sometimes he wrote the little r. Okay, so here will be arctangent. Then sine u will be this one. And how to do that? You can take this easily. U, and here will be x r, right? Because we know tangent u will be x divided by r. Then we know sine u will be this one, x divided by here. And this distance will be x squared, r squared, and root. So sine u will be this one, x divided by, here just take the r out, so that's why it will be in this form. So sine u will be here, so sine u and divide by r squared, and then we can have this form. Then we can back to check. So this will be this plus c, So that's why we can take the boundary 0 to half of length L divided by 2. Okay, so that's all we have. So next Monday I would try to take one of the example as a quiz. So today you must know how to calculate the electric field of the dipole at this position, at this position, and at this position. And also the electric field of this line charge at this position and at this position. These will be the same like this. But try to be careful. This one won't be the same with this. Well, the magnitude will be the same, but the direction will be different. So be careful of that.